In this example, we're given some data here in the table that compares the height and the weight between of 5 different patients at a particular hospital. Now, if we look at the plot, we can try and guess whether or not we see a correlation here. In this graph, to me, it looks like there is a positive trend here, that as height increases, weight is also going to increase. So I am going to guess that we're going to find a strong positive linear correlation. That's just kind of observing the graph of the data, the scatter plot of those data to make that guess. Now, to actually get a more concrete answer, I can perform the linreg t-test here using the data in these two columns. So I'll take the height here in the x and the y here, or the weight in the y column, to run the linreg t-test. Right, so I can enter this data into L1, for instance, enter this data into L2, and then we'll run the test on those two lists. You'll notice that it gives me an R value of 0.903 when we do this test. And so I can compare that with the critical value that we would get from the table here. In this case, we're using a 0.05 significance level. We have a sample size of 5 data. So I get a critical value of 0.878 using the table that we had in the previous slides. So based on that, it looks like here we're going to fall within the critical region where we can reject the null hypothesis, since here 878 would be the critical value, say around there. And then the R value that we get seems to lie within that critical region there. So therefore we can reject the null hypothesis and we can conclude here that there is a positive correlation. So this R coefficient that we've computed here is large enough, it's close enough to 1 here, that we can conclude that there is a strong positive correlation. And notice that also when we perform the test, it gives me the line of best fit. Notice the very first thing it writes at the top is y equals a plus bx. And that would be the coefficients a and b that they give us below. So if I look below, I can find the values for a that they give me here would be negative 359.79. So I'm just going to round that to three significant figures. So that would be negative 360. And the value of b that they give me below would be 7.75. So my line of best fit here, remember I'll write y hat equals negative 360 plus 7.75x. Okay, so that actually would be a line here that passes through this data, that fits the data as close as we can. And how would we interpret the slope? Well, in this case, the slope is 7.75. So that tells me that for each 1 unit increase in the x variable, we expect a 7.75 increase in the y variable. So we can say it this way: each inch for each 1 inch increase in height, we expect about a 7.75 pound increase in weight. Right, so thinking of that as telling us the pounds per inch. So 7.75 pounds increase for every 1 inch increase in height. So that's an important thing, is to make sense of how we interpret the slope in these problems. Right, so for every 1 unit increase in the explanatory variable, on average, there is an increase or decrease of slope units on the response variable. And our y-intercept tells us essentially where the data starts. So when the explanatory variable is 0, then on average the response variable is whatever that y-intercept value is, b0. Right, and we've done this a few times already, right? The Lin-Reg t-test. And what we want to look at now is using the output there in particular. It's going to give us a bunch of things, but we're using the R value to determine whether or not we have a correlation. And then they give us the equation of the line of best fit in this form here, where they tell us A and B. So we can get the coefficients of our equation of the line of best fit. And with that, we can then try and use that line of best fit to help us make predictions about the y values based on some given x value.